Welcome to In-Silico Trials Real Impact, the In-Silico UK podcast that's revolutionizing the way we think about medical innovation. I'm Professor Alejandro Frangi from the University of Manchester, and I'll be your guide through this fascinating world of in-silico technologies. In each episode, we'll dive into cutting-edge research and groundbreaking news that are shaping the future of medical product development and regulation. From computational modeling to simulated clinical trials, we are exploring how digital approaches are transforming healthcare, making it safer, more efficient, more equitable, and incredibly precise. So, whether you're a researcher, regulator, a member of the public, or a patient representative, or simply curious about the future of medicine, tune in as we unravel the complex world of in-silico methods and their real-world impact. Get ready to discover how computer-simulated trials are leading to very real breakthroughs in patient care. In-Silico Trials, Real Impact, where algorithms and data are saving lives. Let's begin.
Welcome to the deep dive. You're here because, well, you want to get a grip on complex topics, fast and properly, right?
Exactly. We know time's short.
And today, we're diving into something pretty fundamental, actually. It's called model evaluation.
That's right. It sounds maybe a bit technical, but it's basically the step after you've built a model, say, for weather or economics or, anything complex where you try to figure out formally, how good is this thing, really?
And it's crucial, but maybe not always.
Yeah.
Clearly defined or talked about.
Precisely. People build models all the time in science and engineering, but how we decide if they're actually any good? Well, that's what we're unpacking today. We're looking at different ways people think about what makes a model good based on our sources.
Yeah, so our mission for this deep dive is to explore these different ideas about model quality and the challenges you run into trying to figure out if a model is actually, up to snuff. We'll touch on how this plays out in a few different fields, too.
Okay, let's get straight into it then. What does it actually mean for a model to be good? Our sources suggest there are, broadly speaking, 3 key ways to think about this.
3 ways. Okay, what's the first one?
So the first perspective is thinking of quality as accurate and comprehensive representation. You could call it the mirror view.
The mirror view. Like it should perfectly reflect reality.
Pretty much. The core idea is that a really good model mirrors its target system, the real world thing it's supposed to represent. Every part, every characteristic, every relationship. It should all be there, and it should be accurate.
Okay, so it's about completeness and accuracy above all else.
Exactly. And this view is often sort of implicit when people are building models. If you think this way, any simplification, anything you leave out, that automatically makes the model worse, less good, regardless of what you actually want to use the model for.
Right. It's all about capturing everything. Total thoroughness. Okay, that's one view. What's the next one?
The second perspective shifts the focus a bit. It's about quality as relevant similarity.
Relevant similarity. So not a perfect mirror then.
Not necessarily. Here, the idea is that a good model just needs to be similar enough to the target system in the ways that actually matter for its specific purpose.
So the purpose is key here. Like what you want to do with a model dictates what counts as good enough.
Exactly. Whether you're trying to predict something or explain how something works, that determines which similarities are relevant. And importantly, from this perspective, idealizations, simplifications, even omissions, they might be perfectly acceptable.
Or even helpful.
Sometimes, yeah. The sources mention this thing called artificial viscosity used in fluid simulations.
Yeah.
It's technically distortion. It's not real in the same way, but it actually helps the model make better predictions about shock waves.
Huh. Interesting.
Or another example, sometimes modelers might deliberately leave out a known causal process in a simulation.
Why would they do that?
Well, to see what happens without it. It helps them understand how important that process actually is to the overall outcome. So yeah, relevant similarity is a big idea. Thinkers like Gere, Teller, and Weisberg have really pushed this.
So the takeaway is, it's not just, is it accurate? Yeah. But is it accurate or similar enough for this particular job?
That's the core of it.
And you mentioned Weisberg. Something about weighted features.
Yeah, Weisberg's weighted feature matching account, it's a way to try and formalize this. Think about comparing cars. If you need a family car, you weight safety and passenger space much higher than, say, 0 to 60 time.
Right.
It's similar for models. You identify the key features of the real-world system relevant to your purpose, and you weight them by importance. Then you see how well the model matches on those weighted features.
But I guess the tricky part is deciding on the weights.
Yeah.
And figuring out what's similar enough.
Absolutely. That's a real challenge, defining sufficiently similar. It often involves judgment calls.
Okay. So we have the mirror view and relevant similarity. What's the third perspective on model quality?
The third one is quality as fitness for purpose. This view really leans into the idea of models as tools or artifacts.
Like a hammer or a screwdriver?
Kind of, yeah. A good model is one that's suitable for the specific job at hand. And crucially, this isn't just about how well it represents the target system. It also brings in practical considerations.
Like what?
Things like usability. How easy is it to actually use the model? Manipulability. Computational tractability, does it take forever to run? And even cognitive accessibility, can people understand what it's doing?
So how user-friendly it is, how practical it is,
Yeah.
that becomes part of its quality.
Exactly. Sometimes simplifying a model, even if it loses some representational accuracy, might make it better overall if it aids understanding or makes it usable in a particular context. This is super important when dealing with really complex systems.
Makes sense.
People like Caswell and Nutilla, and also big reports from, say, the National Research Council, especially in environmental science, they emphasize this view when models are being used to inform decisions, like policy decisions.
And our sources mentioned a kind of subdivision within this fitness idea.
Yeah, that's a good point. There's a slight nuance. Some researchers, particularly those working with, say, climate models or hydrological models, people like Bomberger or Bevan, they talk about adequacy for purpose.
Adequacy for purpose, how's that different?
It's still about the purpose, but the focus is a bit narrower. It's mainly about whether the model represents the target system accurately enough to provide the specific information needed for that purpose.
Yeah.
It links back more closely to that relevant similarity idea.
Okay.
The broader fitness for purpose view, you could say, also explicitly includes those other factors we mentioned: usability, computational cost, and so on.
Right. And that computational cost thing seems huge in engineering.
Oh, absolutely. In engineering, fitness for purpose often strongly involves computational demands and ease of use. A theoretically perfect model that takes 6 months to run on a supercomputer might be useless if you need an answer by next week for a design choice.
Yeah, okay.
And this is where engineers talk a lot about verification and validation. V&V, they often call it.
Verification and validation, what's the difference?
So verification is basically checking the math and the code. Is the computer code correctly solving the mathematical equations the model is based on?
Okay, checking the implementation.
Right. And validation is checking if those equations themselves are actually a faithful representation of the real-world phenomenon you're trying to model. Does the model, as designed, accurately reflect reality in the relevant ways? People like Overkampf and Roy have written extensively on this.
Got it. Code versus reality check.
Although, it's worth noting, someone like Winsberg argues that in practice, verification and validation are often much more intertwined than that simple split suggests. You often can't fully separate them.
Okay. So these are the three big ways of thinking about quality: mirror view, relevant similarity, and fitness for purpose. How does this then translate into actually doing model evaluation? What's the process look like?
Well, the core aim of evaluation is always to gather evidence about the model's quality, viewed through whichever of these lenses you're using.
Evidence. Where does that come from?
Usually two main places. First, the model's composition, its ingredients. What assumptions does it make? What equations does it use? What data went into deeming it?
Okay, what it's made of.
And second, its performance. How does the model behave? What kind of outputs or predictions does it generate? How do those outputs compare to real-world observations?
Composition and performance. Makes sense.
And it's really important to remember, this evaluation thing, it's often not a one-shot deal. It's usually iterative. You evaluate, you find issues, you maybe tweak the model or adjust how you use it, then you reevaluate. It's a cycle.
Right. So let's connect it back. If I'm taking that strict mirror view, how do I evaluate?
Okay, with the mirror view, you're focused on identifying any omissions, anything real that's not in the model, and checking the accuracy of everything that is included. You'd compare model outputs to observational data for, ideally, all available outputs.
Trying to find any discrepancy.
Exactly. Any mismatch suggests the mirror is flawed. Sometimes people try to boil this down to an overall credibility score, but a word of caution our sources raise. Even if a model seems generally credible overall, That doesn't guarantee it'll be accurate for a very specific question you might want to ask it.
Good point. Okay, what about evaluating from the relevant similarity perspective?
Here, the evaluation gets much more targeted. You're selective. You only scrutinize the aspects of the model's composition and performance that are directly relevant to its intended purpose.
So back to that animal model for toxicity.
Right. You'd focus on, say, whether the key biochemical pathways involved in metabolizing that toxin are represented similarly in the animal model as they are in humans. And you'd check if the animal's observable response to the toxin mirrors the expected human response.
But you wouldn't care about, I don't know, its fur color or something completely unrelated.
Precisely. Lots of aspects of the model become irrelevant for that specific purpose.
Okay. And evaluation using the fitness for purpose lens.
This is the broadest approach. You're looking at the whole picture. The model's relationship with the target system, yes, but also its relationship with the user and the context of use.
So the evidence could be quite varied.
Definitely. Evidence might include how well it matches observations for key outputs, of course, but also things like how easy is it for the intended users to operate the model? How fast does it run? How interpretable are the results?
Like that algae bloom model example.
Exactly. For that model, part of its evaluation might involve checking if local water managers find it easy to adjust the inputs and if it provides forecasts quickly enough for them to act. That's direct evidence of its fitness for their purpose.
Okay, this clarifies how the perspective shapes the evaluation.
Yeah.
But it sounds like actually doing this evaluation isn't always straightforward. Our sources mention some hurdles, challenges.
Oh, absolutely. There are some significant challenges that come up repeatedly in practice.
Like what? What's a big one?
Well, a major one is often just the lack of observational data, especially under the specific conditions you're interested in.
Can't compare if you don't have anything to compare it to.
Right. Think about climate models again. We want to know how the climate will behave in 2050 under certain emission scenarios. But we don't have observations of the climate in 2050. We have past data, but the future might be different in important ways.
So you're extrapolating, and it's hard to validate that extrapolation directly.
Exactly. And there's a related issue. Models can sometimes be tuned or calibrated to match the existing data really well, but that tuning might actually make them less accurate when faced with new conditions they weren't tuned on. It might mask underlying problems.
Right. Overfitting to the known data. Okay. What else?
Another big challenge is model opacity. Black boxes.
Meaning they're too complex to fully understand.
Yeah, especially complex computational models with lots of interacting parts, maybe nonlinear relationships. Even the developers might not fully grasp why the model produces a specific output. It just does.
And if the developers struggle, it must be even harder for someone else trying to evaluate it.
For sure. This opacity makes it really difficult to connect the model's overall behavior back to the fidelity of its individual components. Is it getting the right answer for the right reasons, or is something weird happening inside? And it gets worse if the documentation is poor, or if there are lots of sort of ad hoc adjustments made during development that aren't clearly explained.
Hidden assumptions or tweaks.
Right. And related to that, sometimes non-epistemic values like social or political preferences might have influenced design choices, maybe unconsciously, and an external evaluator might have no way of knowing that.
Okay, lack of data, opacity.
What else?
There's also an issue sometimes called holism in assessment.
Holism, meaning you have to look at the whole thing together.
Pretty much. The idea is that you can't always judge the quality of the overall model just by looking at the quality of its individual parts in isolation.
Why not?
Because errors can compensate. One part of the model might have an error that pushes the result in one direction, while another part has an error that pushes it back the other way. So two wrongs might accidentally make a right, or at least a less wrong overall result.
Exactly. Or the way the model is used within a larger workflow might compensate for internal model flaws. Think about a model predicting university application success. Maybe the model itself isn't perfect, but the admissions team uses its output as just one factor among many, and their own judgment compensates for the model's weaknesses. So assessing just the model component might give a misleading picture of the quality of the final decision.
That makes evaluation much more complicated. You can't just tick boxes for individual parts.
It does. It means focusing too narrowly on one component can be misleading. Some philosophers even talk about holistically distorted representations models that are wrong in detail but somehow work well as a whole.
Wow. Okay. And one more challenge you mentioned earlier, trying to actually quantify quality. put a number on it.
Yes, that's another tough one. How do you assign a score, especially considering the model's composition, its internal structure, and assumptions? How much does getting a particular mechanism right contribute to the overall quality score?
That weighted feature thing seemed like an attempt.
It is for the relevant similarity view. But as we said, assigning those weights, deciding which features matter most and how much, and avoiding double counting the influence of related features. It's really difficult.
So what do people do? Just focus on performance.
Often, yeah. If you have several models that seem roughly comparable in their basic structure, you might focus on comparing their performance, how well their outputs match observed data. But even that is tricky.
How so?
Well, there are usually many different ways to measure the fit between model output and data. You could look at average error, maximum error, correlation, error in the timing of peaks, tons of metrics. Which ones do you choose?
And different metrics might rank the models differently.
Precisely. And how do you combine these different performance metrics into one overall judgment? There's rarely a single obvious best way to do it. This all leads to uncertainty about how good a model is relative to others, and uncertainty about how good it is in an absolute sense.
Okay, so evaluation is complex, faces hurdles like data limits, opacity, holism, and quantification issues. Given all of that, how do evaluators actually arrive at a final judgment? A summary statement about the model's quality.
It's often not a simple formula. One way to think about it, which seems common implicitly, is sort of like informal Bayesian reasoning.
Bayesian, like
Yeah.
updating beliefs.
Yeah. Each piece of evidence you gather from looking at the composition from performance tests either builds your confidence or reduces your confidence in the hypothesis that this model is good enough for purpose X. It's a gradual accumulation of confidence based on diverse lines of evidence.
So more of a judgment call based on the weight of evidence.
Often, yes. Another approach, maybe more structured, is to try and pre-specify acceptance criteria.
Like a checklist beforehand.
Kind of. You define upfront. If the model meets criteria A, B, and C, which might relate to its structure, its performance on specific tests, maybe its usability, then we will consider it adequate or fit for purpose. This is sometimes done in engineering contexts where accuracy requirements might be set, or in policy areas like water management.
But I imagine setting those criteria is hard, and then proving the model meets them.
Extremely hard in many complex scientific domains. How do you know in advance exactly what level of performance on which specific metrics guarantees the model will be reliable for a novel future application? It's often very difficult to specify those criteria confidently and then demonstrate rigorously that they've been met.
So it often comes back to expert judgment, weighing different pieces of evidence, warts and all.
That seems to be the reality in many cases, yes. A careful synthesis of the available evidence, acknowledging the uncertainties.
This has been incredibly illuminating. It really drives home that model evaluation isn't just a technical checkbox exercise. It's deeply tied to why we're building the model in the first place, and it's fraught with genuine challenges.
Absolutely. It's a really fundamental part of the scientific and engineering process, making sense of these tools we use to understand and increasingly shape our world. But yeah, it's complex.
So thinking about this for our listeners, when you come across information or a forecast or maybe a policy that's based on some kind of model, maybe pause and think, what does it really mean for this to be reliable?
Mm-hmm.
Given these different ways models can be judged as mirrors, as similar enough tools, as fit-for-purpose artifacts, what questions should you maybe be asking about the models that influence decisions affecting you?
That's a great takeaway thought. What underpins the claim of reliability?
Exactly. Maybe this deep dive sparks some curiosity to look more into the philosophy behind it, or maybe see how evaluation plays out in a field you're particularly interested in.
Lots to think about there.
Definitely. Well, thanks for joining us for this deep dive into the world of model evaluation.